to our next session. We're very pleased to welcome Paul Busch from the University of York to give our third tutorial of today and yesterday, which will be on qubit uncertainty.
Thank you, and thanks for the invitation to give me that opportunity to talk about the latest developments on quantum uncertainty this week. Here is a list of items I hope to cover, at least more or less. Let's not dwell on it for now, these are the chapters to cover. My plan is, first of all, to review the origins of what we call measurement uncertainty relations. This is as opposed to the uncertainty relation that everybody knows from quantum mechanics textbooks, which is about preparations primarily. I'll come to that distinction shortly. So there is a second dimension, if you like, to Heisenberg's uncertainty principle, which we capture here with that term measurement uncertainty as opposed to preparation uncertainty. I'll do a bit of a review of the controversy that has been going on over the last couple of years, about 10 years or so, over the validity of measurement uncertainty relations. There has been a claim of a violation of Heisenberg's uncertainty principle, and that relates to those relations that had never been proven for many decades. I'll then focus on qubits to illustrate the concepts that we need to formalize measurement uncertainty, and to give you some examples of measurement uncertainty relations. So that's basically that. I'll also scrutinize a failed attempt to formalize these relations, and accordingly then the plan was to disprove Heisenberg, as those relations had actually been mathematically proven to be correct and experimentally verified, confirmed. There is a question as to what this all means and how it relates to what I'm going to show you here today or tomorrow. So that's about it. And then back to Heisenberg 1927, where this all began. This is a brief account of Heisenberg's paper that he wrote in that year, as there was a big concern over the new formalism of quantum mechanics, particularly the infamous commutation relations for operators or matrices that were taken to represent physical quantities or then observable quantities, as Heisenberg introduced the term. These commutation relations were seen as something rather formal, and the question was what that meant operationally. There was a strong sense immediately that there was a severe constraint on defining or measuring position and momentum simultaneously, for instance, which was coming as quite a shock at the time. And so Heisenberg was concerned to address these issues and wrote this very fruitful interpretational work. He starts off more or less in the paper with what has become known as the Heisenberg microscope, as an illustration of the fact that if you use a microscope to find the location of a particle, say an electron, by shining light on it and observing the light, then that involves an interaction, and hence as they called it, uncontrollable disturbance. That has become known as the Heisenberg effect. And if you read the paper, you find there's a lot of semi-classical reasoning going on, very informal arguing, and hardly anything by way of proofs. But the microscope has become the paradigm for the uncertainty. The closer you look at the electron, the harder you disturb it, the more it gets disturbed, and so you can't know its momentum, so the story goes. And here it's in Heisenberg's words: let Q be the precision with which the value Q is known. Q1 is, say, the mean error of Q, therefore here the wavelength of the light. Let P1 be the precision with which the value P is determinable, that is here the discontinuous change of P in the Compton effect. Then according to the elementary laws of the Compton effect, P1 and Q1 stand in the relation. And here it is. This is Heisenberg's way of writing the uncertainty relation. He didn't speak about a principle, but this is the relation, the reciprocal relation between the errors of the Q measurement and the error with which P can be known accordingly. He relates this with a twiddle to Planck's constant, and the twiddle gets never defined. So there we go. And then he goes on to prove this. He says this is a straightforward consequence of the commutation relations. QP minus PQ equals IH bar. So he knows all this. This apparently was in the air, and yet he doesn't really prove it. There is clear reference to error and disturbance. A proof is sketched only for what we now would call the preparation uncertainty relation for the case of a Gaussian minimum uncertainty wave function. So he refers to the transformation theory, carefully avoiding speaking of Schrödinger's wave functions, which the Copenhagen camp didn't like at the time. But it's effectively what we know as the Gaussian wave packet for a particle. At that point, it's becoming a bit more precise in pointing to the root mean square deviation of the distribution. That's taken sort of as the error in a position measurement. At least this is the words Heisenberg uses. And then he goes on to say that accordingly then, taking the Fourier transform, you get the momentum distribution, and its width represents accordingly the uncertainty with which momentum can be known. Well, that argument in itself is very sketchy, and it begs making precise. And if you add a little bit to it, then it actually does make sense. So my way of making sense of it is, suppose you start with a particle with a well-defined momentum. So your delta P is very, very small. Think of a plane wave incident into the microscope, and then you observe this. And if you then assume, which is perhaps a fair assumption, that Heisenberg is thinking of what now is called a von Neumann type measurement or a projective measurement, then the particle would be forced into a near eigenstate of position. You could represent that by a fairly narrow Gaussian distribution. So if you have that, then of course you have re-prepared the system, and its momentum distribution is no longer as sharp as it was, but rather has been widened so as to satisfy the preparation uncertainty relation. So here is in that kind of description, there is some justification for speaking of the interplay between measurement accuracy, which relates to what's being prepared, and disturbance, which then comes as a consequence. So that's a way in which we can, if we like, formalize this argument in modern measurement theory. If that was the whole story, that would be poor. We would like to see a statement of measurement uncertainty relations where one is not dependent on specifics of the measurement processes, not dependent on restricting measurements to projective measurements or quasi-projective measurements, but one would like to see a statement in full generality and in a model-independent way, of course. So that's the program that has been waiting there for several decades. And it was only in the 1970s, 80s that things got going. I'll go over a timeline in a bit, so let me not go ahead of myself here. There is rather informal, as I said, reference to root mean square error as standard deviation of the Q distribution. So there is a mixing up, a conflation of measurement error and preparation uncertainty. So these were all points of criticisms that had been made along the way. But let's just distill out of Heisenberg's paper what I see in it. And that is the Heisenberg uncertainty principle in two guises: the preparation uncertainty relations that have become textbook, standard textbook content, and the measurement uncertainty relation. So the first one is preparation uncertainty. We have a state, a wave function representing a particle, then there's a width to the Q distribution, a width to the P distribution, and we can take suitable measures and would expect there to be a reciprocal relation. So that's what we know how to get out of quantum mechanics. As far as measurement uncertainty relations go, there are still two variants. One for the errors that you have in joint attempted measurements of position and momentum, and that would be the second relation. Or if you want to assess the disturbance of one variable as a result of the measurement of another, then for position and momentum you get something like this. The error in the position measurement should be in a reciprocal relation to the disturbance of the momentum measurement. So that's the program, if you like. This is what one should investigate, and that has been investigated by now, in order to see what quantum mechanics has to say about that. So here's just a quick quote from Wolfgang Pauli, who expressed his concerns in 1926 about the commutation relation. One may view the world with a pi, and one may view it with a qi. But if one opens both eyes simultaneously, then one gets crazy. So that was then, and a year later, about a year later, in a letter again to Heisenberg, on reading Heisenberg's paper, Pauli said, "Day is dawning in quantum mechanics." So this was a big step, perceived immediately as a big step forward, what Heisenberg had to say in 1927. Some early developments for preparation uncertainty. There is Kennard. Right away in 1927, he happened to be in Göttingen when Heisenberg was doing this work. And Weil in 28 in a book, they gave this more precise relation. There was a clear definition of what we call the standard deviation for the uncertainties. Kennard was conceptually quite clear, very clear about the distinction between preparation uncertainty, which characterizes states, and measurement uncertainty, which characterizes measurements. But then when it goes on to formalize what is available and what is feasible at the time, and that is the uncertainty relation for position and momentum. Robertson in 1929.
So what's the difference between pi and delta p?
Well, the pi is the notation in Kennard's paper, so it's √2 times the standard deviation.
Oh.
And that is why they get
Okay.
h bar rather than h bar over 2.
Fine.
So it's just notation really. Okay, so then Robertson 29, this is the textbook inequality that we all know, and a refinement by Schrödinger. And all this is just a consequence of the Cauchy-Schwarz inequality in Hilbert space. That's a quick way of proving these, at least for bounded observables. That's rigorous. So what you see in Schrödinger's relation is the two terms, the right one on your side, the commutator term, the expectation of the commutator squared, and the other term is something like a correlation term, which is also there if you look at classical random variables. Okay, so that was all well established around 1930. There have been early denials of the measurement uncertainty relation, probably the first one by Popper in 1934, who gave an experiment that can count as a precursor of EPR, really. And there was an instant rebuttal by von Weizsäcker. This was in Zeitschrift für Physik or Naturwissenschaften. I should have given the quote. But that's what's there. Einstein, Podolsky, Rosen. They used the correlations in the EPR state to say one can infer simultaneous sharp values of position and momentum. I'm not going into the discussion of that. Ozawa actually goes along with this. There's much to say, but I won't on this occasion. Then in 1967, Park and Henry Margenau, they referred to the time of flight measurement method, which gives you maybe initially a fairly well localized particle, and then at a later time you measure where the particle is, and knowing the time, knowing the distance, you have momentum. So yeah, what's with that? And then even still later, Aharov and co-workers came up with pre and post selected situations where in between you can infer that conditionally on what's going on with pre and post selection, you will be able to, or will be more or less forced to assign definite values to spin x, y, and z at the same time between those selections. So there are these arguments against measurement uncertainty relations, and if you look at textbooks, it doesn't help much to see what's really going on. Usually preparation uncertainty and measurement uncertainty are conflated. There's really no reflection in textbooks, not much at least as far as I can tell, on how to define measurement errors or disturbance. And accordingly then you can have the opposite claim, namely preparation uncertainty and measurement uncertainty are in some books clearly distinguished. They say this is not the same stuff. But because measurement uncertainty is not preparation uncertainty, then some people go on to say, well, then it follows there is no limitation to joint measurements without further analysis. Or examples like those that I showed. So I'll show you how one can take a different view to that. Now, here a word on Heisenberg according to Ozawa. This is an interesting one that goes for more formal, rigorous challenges to the measurement uncertainty principle. Well, here are the error versus error or error versus disturbance relation according to Ozawa. Ozawa has a specific definition of epsilon here and of eta, state-dependent errors and disturbances. And he sort of proposes a generic statement like this: the product of the errors should be bounded below by commutator term. And likewise, the product of error and disturbance in a sequence of measurements should be bounded like that. And then he goes on to say, well, we will call this the Heisenberg uncertainty principle. So just, well, he tries to give some evidence why he thinks this could be read out of Heisenberg's papers, but we have failed to follow him in that. I'll say more about that. If you look into Heisenberg's paper of 1927 or his book of 1930, the Chicago lectures, where he lays these ideas out in more detail, there's nothing like these relations. It's always conjugate quantities, position and momentum, and concrete examples rather than formal statements with formal definitions of error and disturbance and proofs. There's none of that there. In any case, in Ozawa's formalization, as Ozawa knows and proves, these relations are only of limited validity. Hence, according to Ozawa, because these must be the things that Heisenberg had in mind, Heisenberg got it wrong, and Ozawa is going to prove a violation of Heisenberg. So that is how the argument goes. Credit goes to Ozawa for being probably the first of having started to give formal definitions of, proposed definitions of measurement error, measurement disturbance, and formulating and proving relations based on these that are model independent and, as he says, universal uncertainty relations. So that was happening for the first time in the early 2000s, as late as that. Quite a few of us had been going on with this theme on and off, giving models of joint measurements or sequential measurements, illustrations of forms of measurement uncertainty relations. So at the level of models, we had a lot of evidence in the 1990s already of measurement uncertainty relations pretty much in Heisenberg's spirit, if that is an allowed phrase of thought. But Ozawa was the first to give a formal definition of errors and prove some relations. And that's Ozawa's correction here. You see there are three terms that add up. Error times, here I've taken the disturbance version of it. Error times disturbance for A and B plus the error of A, of the A measurement, times the standard deviation of the B variable plus the standard deviation of the A variable times the error for the B variable. All these taken together are bounded by the commutator. That is a correct mathematical relation, which we can prove, could prove if I gave you the definition of epsilon and eta. So for now, trust me on this. I'm convinced, and I'm going with Ozawa, this is a correct, mathematically correct relation. And I'm giving the definition of these terms later when I need them. So here you see, first of all, of course, there is no reason for epsilon times eta not being allowed to be as small as you like. And again, we'll see examples where that can be arranged. Experimentally confirmed as well, all this. But I hold that before we buy this and accept this as a measurement uncertainty relation, we have to look more closely, and that is what I'm going to try to do today and tomorrow. So, following Ozawa's papers from 2003 and 2004 and onwards, in 2012, the first experimental confirmations were given, and you see statements there such as Heisenberg's original relation is valid only under specific circumstances. Okay, Heisenberg's original relation, you may just about see it here, is epsilon of q, eta of p, twiddle h bar over 2, so that's already translated into modern times. Then they go on to say the general form of Heisenberg's error disturbance relation is epsilon of a eta of b greater or equal the commutator term. But they point out, as Ozawa had already shown at the time in 2012, Heisenberg's proof, which I have difficulties finding, used an unsupported assumption. So that is Ozawa's reconstruction of a proof of Heisenberg's relation. And that has an assumption that, yeah, it's unsupported. And if one gives that up, then they get Ozawa's rigorous and new universally valid relation, the one I just showed you. So that's the story in 2012. This has gone through the press worldwide with the BBC reporting Heisenberg uncertainty principles stressed, or in Germany the great Heisenberg got it wrong, and then the physics journal thought in our proof of Heisenberg's error disturbance relation, well, finally we were rescuing Heisenberg. So that's the fun going on, and yet, yeah, they're not agreeing still. So instead of, one point I want to make is, instead of putting words into Heisenberg's mouth or reading Heisenberg's mind, if you like, we could look at the spirit of the thing, of the principle, and hence we could look at what does quantum mechanics tell us about the possibilities of measuring jointly incompatible quantities. So, what I would still dare to call a statement in Heisenberg's spirit is this here, that what we are looking for, whether it's true or false, we have to see, is a statement like this: combined joint measurement errors for A and B in an approximate joint measurement are bounded, are constrained by the incompatibility of A and B. We can't measure A and B together. We can try to measure them approximately in some scheme, and then see what the price is for that. This is what I'm going to quantify for you here, and then compare to Ozawa's approach. Well, I was planning to do a quick timeline to try an explanation of why this all has taken so long. And yeah, it's still not common knowledge as you check the textbooks as I did, and as I told you, there are contrasting statements on what's the case or not. The answer in a nutshell is that after Robertson and Schrödinger's work, using the Cauchy-Schwarz inequality, that was so appealing and simple looking and final that seemed to be really the end of it. Preparation uncertainty was sorted once and for all. There was no clear way of connecting that to measurement uncertainty, and not much further thought was spent on that, except in rather singular attempts. But really what was missing at the time was a theory of approximate quantum measurements that then could be used to make sense of trying to measure approximately two incompatible quantities in one scheme simultaneously. And that's really what is missing. And here are the steps that led there. Well, yeah, this is sort of the textbook wisdom again. I think I should have taken this out really. But as it's here, you see, you can put it into prose. The uncertainty principle has nothing to do with the errors in joint measurements, because it's about operations, the spreads of separate measurements. You measure position statistics on a similar example, but separately you measure momentum, get the statistics, and that is the preparation uncertainty relation. And besides, joint measurements of non-commuting quantities are impossible, or some people didn't take that statement, said hence there are no limitations to joint measurements. And then we can play with this sense. Joint measurements of non-commuting quantities are impossible. You have to make that precise and say precise joint measurements of non-commuting quantities are impossible. And if you swap the words around, then you could say imprecise joint measurements of non-commuting quantities are possible. So this is the game we try to play. What's needed is notions of imprecise approximate measurements, measure of error, measure of disturbance, and what have you. So here's my timeline. I said a lot about Heisenberg 1927. So I would like to emphasize here that, yeah, we learn that uncertainty relations are expressing a limitation, and sure they do that. They express an impossibility, and sure that's true. But Heisenberg was quite a positive spirit. He was looking for an explanation of the positive possibility of seeing particle tracks in cloud chambers in view of the commutation relation for position and momentum. This was really what Pauli felt was making them crazy at the time. How can you have that impossibility of seeing position and momentum at the same time, while you do see cloud chamber tracks? So you see particles, elementary particles move on fairly well-defined appearing tracks. Well, today the answer is quite obvious, but at the time I had to think long and hard about this. So for Heisenberg, that the discovery of the uncertainty relations, especially for measurements and disturbance, they were seen as a positive result. There are limits within which I can get coarse-grained trajectories according to quantum mechanics. So that's his motivation, really. Then von Neumann, in his famous book of 1932, gave a proof of the impossibility of joint measurements for non-commuting quantities. And in his book, that is our standard self-adjoint operator view. Self-adjoint operators representing observables, or the spectral measures thereof representing observables. And today we would call these the sharp observables as opposed to all other POVMs, positive operator measures, representing more general measurements. So that was a clear no-go statement, a mathematical proof, and against that we have to attempt to measure how much error we need to allow in order to speak of joint measurements of such incompatible non-commuting quantities. Well, then there was Wigner 1932 coming up with, it was an attempt to define probability distributions on phase space whose marginal distributions are the standard position distribution and momentum distribution for the same quantum state. And he did the maths and came up with a definition of what we now know as the Wigner function. And of course realized immediately this is not a proper probability distribution unless you take Gaussian wave functions. So that is really a concrete confirmation and illustration of the Neumann's theorem, here for position and momentum. Another illustration that it's impossible to construct joint probabilities. There is no sense in which you can have joint measurements, joint observables. What you get is quite a different monster, quasi-probabilities they are usually called. Well, this was Wigner and Moyal in the 1930s. Then Cosimi in 1940 did come up with what is in quantum optics known as the Q function nowadays. That's a proper positive phase space distribution associated with each state of particle. And it has the right quantum mechanical form, expectation value for the state of some operators, giving the density of that distribution. So that was a little step away from formulating POVMs as a representation of generalized measurements. Well, the goal was at the time to find these phase space distributions, to look at classical limits of quantum mechanics, doing thermodynamics and all that. So there was no concern with directly attempting a theory of joint measurements of position and momentum. But this contains the tools to deal with position and momentum, pretty much. So in modern language, what Cosimi has discovered here basically is an instance of what we now know as a Heisenberg-Weil covariant POVM on phase space. But that had to wait for another 20-25 years before it was properly formulated. Again in 1940, Neumark, now spelled as Neimark, introduced semi-spectral measures. This was a concern in Hilbert space operator theory, the realization that there were symmetric operators that did have no extension to a self-adjoint operator in the given Hilbert space. And Neimark realized then that there are natural extensions of such symmetric operators to self-adjoint operators if the Hilbert space is allowed to be enlarged. And there's a canonical procedure, that's the Neimark dilation theorem. So that's the mathematical language emerging and being developed, which we now use for POVMs as description of general measurements in quantum mechanics. Then in the 1960s, work in quantum foundations elaborated on this, and there were first ideas on the fact that non-commuting observables may be jointly measurable if they are sufficiently unsharp. So you can't measure position and momentum as they are, spectral measures, jointly, but if you replace them with something similar looking but unsharp, not spectral measures, then there is a possibility of joint measurements. So these ideas were beginning to emerge in the 1960s. First very concrete measurement model is due to Arthurs and Kelly, 1965. They give a concrete coupling Hamiltonian describing the measurement coupling of two particles that are used as probes to separately, simultaneously apply them, couple them to a particle, your object system, so that one probe gives you information about the position and the other probe gives you information about the momentum. Arthurs and Kelly's criterion for this being an approximate measurement, or a good measurement of position and momentum, was that the statistics of the probe pointer observables reproduce, well, not the statistics of position and momentum, but the first moments. So the mean values of position and momentum were captured by these joint measurements. And that was the whole concern at the time. So a very modest notion of joint measurement, just confirming the mean values of the distribution. That's a rather trivial thing from today's perspective, but the model in itself is very significant and important and has provided guidance for much of what came later. Then on into the 1980s, that was the period where models like this and others were developed further, and concepts of joint measurements or joint approximate measurements were being discussed. First realizations of not Arthurs and Kelly's model, which is rather artificial physically speaking. It's Hamiltonian, or interaction Hamiltonian is rather artificial. But in quantum optics there are alternatives, such as homo and heterodyne detection schemes, that lead to, as it were, joint determinations of smeared versions of quadrature components. So that's the quantum optics jargon for what's being measured. Quadrature components are mathematically like position and momentum, and in these experiments it was shown you see smeared versions of those. Smeared versions in the sense of actually having a convolution of position with some probability distribution to show it as a smeared position, and likewise for momentum. And those were then realized in one common scheme, in a proper joint measurement. So quantum opticians in the mid-80s were catching on quite nicely, and were bringing these measurements together with the concepts that theory provided. And then, as I said, in the 1990s, there were first attempts at systematically formulating measurement error and model-independent measurement uncertainty relations. Ozawa introduced his concept in the late 80s, early 90s, his error measure, but only thought of doing model-independent universal uncertainty relations using these concepts in the early 2000s. In between, Appleby picked up the concept, had some very good critical comments about them, and went on to use a kind of fix, which I can explain later when I've defined Ozawa's error. So Appleby was the first to have some sort of model-independent position momentum uncertainty relations, pretty much in the spirit of Heisenberg. But as I'm going to show, the concept, the quantification of error has its flaws and problems, so we have to be cautious with that attempt. And then since 2004, the battle is raging, as it were. Ozawa's inequality appeared, and immediately Reinhard Werner and ourselves independently came up with critical papers, and we tried to influence Ozawa's thinking on his work, and we haven't been successful. So, since 2012, it got heated up by there being new experiments, and then quite some rise of activity in formulating new measurement uncertainty relations. So this is now quite an active field, as it were. And I want to go on now to start showing how to formalize things. So here a quick rundown of the essential measurement theory concepts that we need. So here's, in a nutshell, motivation for the concept of a POVM, a caricature of a generic type of experiment where you prepare, you measure, you register, count statistics, and hope for the best that the statistics agree with your theory's predicted probabilities. So that's here written out. Pi is a concrete preparation device or procedure, sigma measurement, and then we have these bins counting values and estimating probabilities. So in the formula, then we see here in the quantum description, the quantum state representing all equivalent preparation devices, so equivalence class of preparations, where two preparations are equivalent if they give the same statistics for all measurements. Likewise, you can take classes of all measurements that provide the same statistics for all states, and those we formalize here in terms of what we call observables or positive operator valued measures. So that's my notation. If it's a discrete case, you have values attached to or assigned to positive operators, and the probabilities for the outcomes are given by the quantum mechanical formula trace of rho times E sub I. Yeah, states then are operators on Hilbert space H, which have the property of being positive, bounded by 1 naturally, because then the trace is typically set to 1. Effects is my preferred name following Ludwig's terminology for the positive operators that represent observables that are elements of a POVM. That's another word for it, POVM elements. And sets of effects, collections of effects, adding up to the identity, make up a POVM representing a measurement. So each measurement outcome associated with one of those EI operators. The sum of the EI being 1 reflects the fact that for each state, the probability distributions P sub E sub rho are normalized probability measures. Well, further concepts are state changes, which we formalize in terms of instruments. These are state transformation valued measures, that's the fancy mathematical term. For each measurement outcome, there is a linear trace non-increasing map so that rho gets sent to the output state in the measurement, assuming that there is an output system identifiable with that input system. So the measurement is not entirely destructive, but changes the object. And measurement processes, that's the sort of most detailed level of describing measurements as dynamical processes as a quantum mechanical process. So we have a Hilbert space associated with the apparatus or measuring probe, H sub A. The probe system is supposed to be in an initial state that we fixed phi. There is a unitary map that describes the coupling interaction between the object system and the probe, and there is a pointer observable for the probe, Z sub A. And I'll come back to that. Just a quick look at how this generalizes. An observable could be a continuous quantity, and to encompass that, we allow for general measurable spaces, a value space omega, sigma, a sigma algebra of subsets so that we can do probability theory. Observables then are just operator valued measures. That's expressed positive operator valued measures, which are normalized and satisfy the additivity requirement for unions of disjoint subsets in the algebra. and the probabilities then are given in terms of the quantum mechanical expression as we know it. So here a quick look at instruments then. These are again associated operations to each outcome set, and each operation then defined as a map that sends every state to an output state to output state, and that fixes the measured observable. So each instrument induces a P of M by this formula here. The trace of the output state is taken to be the probability for the measurement outcome, and hence the probability for the P of M in the state variable. Yeah, we can make some use of instruments here to illustrate the Heisenberg effect in a very simple statement, if you like. Namely, quantum mechanics tells us if there is no disturbance in a measurement, then there is no information to be gained. So the assumption is, whatever you do, you assume, like we know we can do in classical mechanics, in classical physics, we can measure without ever significantly affecting the object system. So simplistically, we write this really as the non-selective measurement operation or channel that comprises all possible outcomes that shouldn't change the state, whatever the state is. If that's our assumption, then it follows that actually the outcome probabilities are independent of the state. So you don't get any information on the state. And that mathematically means the measured observable is trivial. Trivial, well, you see, the equality of the probabilities over all states, over all pairs of states, means that probabilities don't depend on the state, so the P of M is of that form. It's a fixed probability measure times the identity operator. So these are what I call trivial observables. This is really a way of introducing that concept, which is almost trivial but can be useful to formulating certain results. If you want to see the proof, here it is on one page. Let's squeeze it. Let's quickly go through it. I think I have time. So we assume the non-disturbance for pure states. So P bracket phi means the projector onto the unit vector phi. And we assume that doesn't get changed for any phi. Then using the additivity of the instrument, we have the operation I of x and the operation I of x complement. And by the additivity, then we have of instruments, we have the sum of those two non-normalized states being I of omega of p phi, which is p phi by assumption. And that means, because this looks like, and it is, a convex decomposition of a pure state into two components, well, then you can either have one of the components 0, which is not generic, or else, and even in that case, both components are proportional to p phi, and multiples of p phi. That's a simple convexity argument. You can't decompose a pure state except into itself, into bits of itself. So that's the first conclusion, that generically we must have I of x applied to p phi is already a multiple of p phi. And the factor is the probability of obtaining x in that state. So, next step will then be to show that the probabilities and hence the positive operator measures won't be different. Well, the positive operator measure will be trivial. The probabilities for two distinct states are the same. First, look at phi and psi being perpendicular. Then they span a two-dimensional Hilbert space. In there, you can take another basis of that two-dimensional subspace, take psi and eta, psi not perpendicular to phi or psi, and eta perpendicular to psi. And so both these are orthogonal vectors, and the projections are the identity in that two-dimensional subspace. You can write the sum of the projections like this, and it must be the same as that. And so if you apply I of x and use that result over there, you get this equation down there, where you have the weighted sums of p phi and p psi here, and of p psi and p eta over there. This is writing the same operator, the same self-adjoint operator, in two different looking spectral decompositions. So here we use the uniqueness of the spectral decomposition of the self-adjoint operator to argue that therefore these coefficients must be the same. The spectra must be degenerate. So the operator is still a multiple of the identity in that subspace. And that gives you the equality of all these probabilities. Well, and then you're basically done, because that means if you start with a phi and then take any vector that is not orthogonal to phi, namely psi, then you already have the equality of all the expectation values for each effect E of x. So that is the statement that the P of M E that is measured by this key, by this instrument, is trivial. And you can give the instrument, the form of the instrument is also trivial. It's just not changing the state, and the weight attached to each state after the measurement is just the fixed probability. So that's no disturbance, gives no information. Well, I'm entertaining you here with trivialities. Here is another simple example. This is what we could call a constant channel instrument. So we take a fixed state rho, we take a fixed observable C, P of M, and define the state transformation like this, that every output state is a fixed state, rho naught, and the weight to it is the probability for the observable C on that outcome x. So you can easily check that that defines, that is an instrument that defines the observable C. Of course that is. If you take the trace of the output state and rho naught is the trace 1 operator, then you get the right probabilities for C. But what does that mean for disturbance? If you take now a measurement of B after C, and there is a here. Oh, no, that's all right. This is what is being defined. We take the, I should have written it that way around. This symbol here, I star, I omega star, is the dual instrument, and so this number that I'm giving here, I forgot to give that here strangely, is equal to trace of I of omega rho of times B of y. And then the dual instrument is defined by carrying over the operation to the operator B of y here. So that defines B prime as a new observable given an observable B. And this equation describes how an observable B measured after C sees the state rho. And it doesn't see it directly, but it sees it as if we had measured B prime, which is different from B. And in this case, because the probabilities are always the same, namely fixed by the state rho naught, then we see that B prime actually is a trivial observable again. So if we take a constant channel instrument, then the disturbance is so dramatic that whatever we measure afterwards, of course, contains no information about rho, because what the subsequent measurement sees is just the state rho naught, no reference to rho. So that's it is a trivial result, but it goes for, it helps us to see immediately that for every observable indeed there is, even if only a trivial instrument, in fact, it takes a bit more work to then construct an infinity of instruments for each observable. That's the general statement. So that was a bit of technical work. Let me go with the concepts. Here is the concept of a measurement scheme as I described it earlier, and its purpose then is to capture what happens to the object system, rho, in a measurement, and you can describe that by carrying out the evolution, here written in Heisenberg picture format, afterwards measure an observable B on the object, and that's the expectation that we get for it in the output state of the object. So that implicitly defines the instrument. Every measurement scheme induces an instrument. That's the first twiddle here. And we already had the second twiddle, so that's cast here in measurement theory language. If the B operator is replaced by the identity only, then we just get the probability for E. Well, that defines E. That defines A P over E. So a measurement scheme gives a more detailed description of the instrument, of an instrument. It defines uniquely an instrument, and as such then also uniquely an observable. We make occasional use of that. Here's again a simple example. The swap map as a coupling. The object system and the apparatus system, probe system, are taken to be identical, and then the measurement consists of transferring information about the object into a copy of it, basically, and we do that by the swap. And what happens is indeed here, rho and sigma would get swapped. I've written it here again in Heisenberg picture terms, and what we get, of course, is the system ends up in a fixed output state, what we called rho naught beforehand. Here it's called sigma, the apparatus state. So that's what we see here on evaluating the instrument. The instrument is simply the state sigma embellished with the probability for E, the measured observable. And we get the measured observable by identifying the pointer with E, or taking the pointer as E. So that's a perfect measurement of E, perfectly disturbing, so that afterwards no further information about rho can be obtained. So that was the previous example. Again, I may use that later when it comes to discussing disturbance. So now I'm approaching the question of defining concepts of measurement error, and here I do that by looking at the probability distributions associated with the observables. And here's to begin with, to get us started.